All right, this is Monday, yikes, December 14th, 2020, Aerospace Engineering debrief or reteaching or reviewing on how to find tensions and compressions when analyzing a truss structure. So this particular one is from Truss Reaction Forces 2, problem number 1 that was assigned just to find the reaction forces. In that assignment, we had 200 newtons pushing down. The reaction forces would be 40 newtons pushing up at point B, where the roller is, and 160 newtons pushing up at point A, where the pivot point is. Now, I'm going to go inside and start calculating the actual tensions and compressions for this truss structure. At point B, as in all points, all the forces and all the moments have to add up to zero. If they don't, then this thing is not statically stable and it's going to accelerate in some dimension, either translation or rotation. So at point A, all the forces and moments have to add up at zero. Same thing at B, same thing at C, same thing at every vertex that you can see. I choose to start looking at point B first. I have if I draw just a free body diagram to some sort of scale, and I'm going to make my scale larger now. So let's say that going up almost 2 squares is going up 40 newtons. That's the reaction force going through point B, transmitted from the ground through the roller to vertex B. AB, member AB, is only capable of pushing apart or pulling together horizontally. And no matter how great the force is horizontally, that will have no effect on the force that is perpendicular to that. This is one of the principles I emphasize in my physics course. Motion and forces as well in one dimension is independent of the forces and motions in a perpendicular direction. So anything that's going on vertically is independent of affecting whatever's going on horizontally. So if the ground is pushing up at point B vertically with 40 newtons, member AB can't do a darn thing about it. Only member BC can do something about it. And member BC can pull or push. If it pulls, then it's going to be contributing in the same direction as that 40 newtons. It's going to be lifting it up and to the left at the same time if this is under tension. So member BC must be pushing down and to the right. Pushing down and to the right. So that makes this member under compression, even though I don't know the value of it yet. Now I'm going to go calculate the value. It's pushing down and to the right. The scale ratio of horizontal force to vertical force is the same as the ratio of horizontal distance is to vertical distance physically for that truss member. This particular truss member, and by the way, I'm using 2 squares per unit. So 1, 2, 3, 4, 5 is the scale, and this was 1, 2 is the scale. So for every 2 units of vertical distance or force, there are 4 units of horizontal distance or force. Because we're not going from point A, we're going just this little right triangle here, a vertical component, horizontal component between B and C. There's our 3-minute bell. I'm going to pause. Whoa, 3 minutes of class time just went by, and now I'm going to try to catch up and summarize what I just did. The forces acting at point B caused by the roller were 40 newtons up. So BC must be pushing down by 40 newtons. The magnitudes of the forces are identical to the ratio of the magnitudes of the distances for the forces. So if the vertical component of BC is 2 meters and the horizontal component of BC is 4 meters, the ratio is 2 to 4, which simplifies to 1 to 2. That must be exactly the same ratio as the force components of member BC. So for every 1 Newton of vertical force, there must be 2 newtons of horizontal force. Applying that to member B, 40 newtons being pushed up through the roller is canceled by 40 newtons being pushed down by member BC. But the side effect is that member BC is pushing horizontally with twice as much force, 80 newtons. The hypotenuse is from Pythagorean's theorem. 40 squared plus 80 squared is 89.4 squared. Don't bother putting arrowheads because the news is always right, Mr. Turk's always wrong, but Mr. Turk controls your grade, so therefore just leave them off. And label it C for compression, or T for tension, or N for neutral. Such as, and that's only when it's 0.0 newtons, neutral. Great. So now B has these 3 forces acting on it. The roller pushing up with 40 newtons, member BC pushing down with 40 newtons, member BC pushing to the right with 80 newtons. To compensate for that, I bring to bear member AB and assign it the job of pulling B to the left with a magnitude of 80 newtons. And so there is this member down at the bottom, 80 newtons of tension. Ta-da! Now let's take a look at just point A and see what the heck we can say. We have member B pulling A to the right with a force of 80 newtons. We have the ground pushing up. Oh man, so what is this? 150. I guess I'm not doing this to the correct scale. With a force of 160 newtons. It's not allowed to move. This point has to be statically stable. The sum of all the forces and all the moments acting through this point have to add up to 0. There's only one member working on A that we haven't taken into account yet, and that is member AC. Fortunately, it's a diagonal, which means hopefully it can take care of both of these components in one fell swoop. Looking at its coordinates, we see it is 1 meter to the right and 2 meters above point A. The ratio of these two legs is 2 meters vertical for every 1 meter horizontal of change in position going from A to C. Therefore, the ratio of the forces is also 2 newtons of force vertical for every 1 newton of force horizontal, which is great because when I look at it, this is a ratio of 2 to 1. So I'm very happy to assign C to be pushing A to the left with 80 newtons of force, with the side effect that it's going to be pushing down with 160 newtons of force. So C is actually going along this diagonal. Here's its horizontal component, 80 newtons. Here's its vertical component, 160 newtons. They form two legs of the right triangle. So the square root of 80 squared plus 160 squared means this magnitude is 179 newtons, 3 sig figs. And C is pushing on A. So this is under compression. I have now completed my reaction force analysis for problem 1 from Truss reaction forces number 2. I'm turning that back on. Yikes. Truss reaction forces, homework 2, problem 2. I already leapt ahead because I forgot to hit the record button. Yikes. An applied force of 250 newtons horizontally to the right at an altitude of 3 meters above the ground on this truss means there's a reaction force of 250 newtons to the left. For the moments to compensate, 750 newton meters clockwise is compensated by 750 newton meters clockwise through B. That means the reaction force is 187.5, let's call it 188 newtons up through point B. To have the sum of the vertical forces add up to 0, the reaction force through A must be 188 newtons down. Only after the reaction forces are correctly calculated does it become possible to calculate the tensions and compressions of the truss members themselves. Only after the reaction forces are correctly calculated, acting outside this truss, can you then go inside and look at what's going on with each member. My habit is to start with the roller. If the roller is pushing up with 188 newtons, member AB cannot do anything about it because it's perpendicular to the direction of motion. And forces that are perpendicular to each other don't influence each other. Member BC, it has the job of pushing downward on point B with a magnitude of 188 newtons. When I resolve the displacement between B and C into a right triangle, I see that to scale, for every 3 meters vertically, there's 1 meter horizontal of displacement. That must be the same ratio of the vertical to horizontal forces. So for every 3 newtons of vertical force, there must be 1 newton of horizontal force. And therefore, B is being pushed to the right by 1/3 of 187.5. And my calculator says that is 62.5 newtons, pushing it to the right. Now I have a horizontal force. Oh, by the way, I can now calculate the magnitude of the compression of member BC. It would be the hypotenuse of a right triangle formed by a leg of 62.5 newtons and a leg of 187.5 newtons. So let's do that while it's convenient. 187.5 squared plus 62.5 squared, enter square root, worked out to be 198 newtons. Or if you like, 197.64235338 rounded to 3 sig figures. 198 newtons of compression. That's member BC. All right, well.
Kurt,
Yeah?
Which numbers exactly did you multiply to get 188? Because everything's making sense, but I don't know what number specifically you got to multiply to get 188.
Child, I was solving for the reaction force through point B. The original problem says the only load is 250 newtons acting at a point 3 meters above the pivot point. I back up the load until it is directly above the pivot point, because I'm allowed to slide it along forwards or backwards along its line of action. When it is directly above the pivot point, it very conveniently is a 90-degree angle between the direction of R, which is vertically 3 meters, and the direction of F, which is horizontally 250 newtons. For calculating the moment, the formula is R cross F, which would be 3 meters, is equal to 3 meters times 250 newtons times the sine of negative 90 degrees in this case, because R is taken to be 0 degrees, the direction of R, from the point of from the axis of rotation to the point of application of the force. Of course, that direction is 0 degrees. I'm turning clockwise 90 degrees. So negative 90 degrees. Sine of negative 90 degrees is negative 1. 3 times 250 times negative 1 is negative 750 Newton meters. That is the moment about point A caused by the load being applied at point C. The moments must add up to 0. There's only one location in this entire truss where I can apply positive 750 Newton meters of moment. And that is through point B. R, in going from the pivot point to point B, is 1, 2, 3, 4 meters. The moment has to add up or multiply out to positive 750 Newton meters. So that's equal to 4 meters times the reaction force through B in the Y direction. And ever so conveniently, R is to the right, the reaction force is vertically up, the angle is positive 90 degrees, the sine of positive 90 degrees is 1. I solve for the reaction force through B, and I get 187.5 newtons.
So it was 7 by 4?
Yes.
Isn't that like 10 by 4? Oh, okay, that makes sense.
You have weak batteries on your calculator, child. Test on Thursday. Okay, so I'm still recording, and that's how I came up with that number. This ratio of 3 to 1 is how I came up with that number. Pythagorean's theorem is how I combine these two numbers to get that hypotenuse. And I guess I should already, point out, hey, I figured out member AB must be under tension because A is pulling B to the left with a magnitude of 62.5 newtons. A is pulling B to the left, so B is pulling A to the right with a magnitude of 62.5 newtons. Which one do you want me to do next? A or C? Ariana?
Can you do C?
Sure. And you just go solve these things in whatever order appeals to you. And maybe you only solve part of it and then go to another vertex and figure out something and then come back to this one. I'm going to now take care of point C. I see, I spy with my eye that B is pushing point C up and to the left. It's pushing up with 62.5 newtons of force, because that's what C is pushing down. Oh, I said the wrong thing, didn't I? I'm sorry. The roller is pushing up on B with 187.5. So C is pushing down on B with 187.5. So B is pushing up on C with 187.5 newtons. B is also pushing C to the left with 62.5 newtons. I have three forces acting on point C right now, and I'm not yet looking at member AC. So if I sketch what I have, maybe to some sort of scale, let's say 50, 100, 150, 200, 250. So I have a load of 250 newtons acting to the right at point C. I have 62.5 newtons acting to the left at point C, caused by member BC. I have, let's see, 150. I have 187.5 newtons pushing up on point C. All of this is point C, caused by member BC. So far, so good? Okay. Now, 250 newtons to the right, 62.5 newtons to the left, they partially cancel. 250 minus 62.5 means, oh, you're going to love this, it is pushing with a net force of 50, 100, 150, of 187.5 newtons to the right, and 51, 150, 187.5 newtons up. This is at point C. That's supposed to be a C, not the letter O. Yeah. Okay, 250 newtons to the right, caused by the load. 62.5 newtons to the left, caused by the horizontal component of member BC acting on point C. They take the difference. I get 187.5 newtons to the right. Now there's only one force left acting on point C, and that is member AC. It must be pulling point C down and to the left. And my, oh my, look at the ratio. For every 1, 2, 3 meters that we go to the right, we go 1, 2, 3 meters vertically up. Oh, Sylvina, I know it's boring that you're not taking the test now. Nice going, nice going. Oh, that reminds me. Did all you students actually ever show up? Or are we still missing 2? Oh, no. We lost 1. All right, there's the bell saying it's the end of the period. Children, test on Thursday on this skill. I'm going to attempt to finish this thing up. I had calculated that the forces acting at point C have a net amount of 187.5 newtons to the right, 187.5 newtons to the left. So member AC must be pulling point C down and to the left. Ever so conveniently, it's a ratio of 3 vertical to 3 horizontal. That's the same ratio, 1 to 1, that I'm seeing here. So, member AC must be pulling 187.5 newtons to the left and pulling 187.5 newtons down on point C. The hypotenuse would be the magnitude. So if I take the square root of 2 times 187.5, I get let me do that correctly. The square root of 2 times 187.5 squared is 265 newtons. 265 newtons, and this is under tension. 265 newtons of tension is the reaction, is the truss member AC. Now I turn my attention to vertex A. At vertex A, I have member BC pulling A to the right with 62.5 newtons. I have member BC pushing down, oh man, with 187.5 newtons, pushing to the left with 187.5 newtons. I have the reaction force on the outside of point A. Oh, I'm sorry, I drew this the wrong way. Let's do this correctly. At point A, we can start with the reaction forces. 187.5 newtons downward. Let's make 51, 150. All right. 187.5 newtons downwards. That's going to the pivot point. I said there's a reaction force of 250 newtons to the left. Now, member BC is pulling member A to the right by 62.5 newtons. In addition, member AC is pulling A up and to the right by 187.5 newtons up, and 187.5 newtons to the right. Okay, so all these forces, I'm sorry, I was blocking it. All these forces acting on point A, what are they? I have the load reaction force through A, 250 newtons to the left. I have the reaction force of the ground pulling point A down with 187.5 newtons. I have member member AB pulling A to the right by 62.5 newtons. I have member AC pulling A 187.5 newtons up and simultaneously 187.5 newtons to the right. When I stare at this free body diagram, I'm going to make the bold claim that 187.5 newtons plus 62.5 newtons better add up to 250 newtons, or else it's going to fall down. 187.5 plus 62.5, sure enough, adds up to 250 newtons. And this free body diagram is complete. The analysis is complete. This ends this particular truss structure for complete analysis. We are now totally done. Member A, I should say vertex A, has a reaction force of 250 newtons to the left, 187.5 newtons down. Reaction force at B is 187.5 newtons up. Member AB is tension of magnitude 62.5 newtons. Member BC is compression of magnitude 198 newtons. Member AC is tension of magnitude 265 newtons. Everything is static. Ta-da.